The final electrophilic addition reaction of alkenes that we're going to look at is the hydroboration of alkenes. And we can see that we can couple this with an oxidation as a way of synthesizing alcohols. So let's start with the hydroboration itself that's shown here. And this is the overall generic reaction where some sort of borane compound, whether it's borane itself or a dialkyl borane, which is shown here generically. These reagents will react with alkenes to give the addition of boron and hydrogen across the double bond, simply known as a hydroboration. And there's a couple examples shown below. Here we have a simple 1-butene reacting with borane itself, ultimately producing a trialkyl borane. It turns out all three of the boron-hydrogen bonds in borane are reactive, so three equivalents of alkene can react. There are other derivatives of borane that are available. One very commonly used one is known by this acronym 9BBN, stands for borobicyclononane. And the boron-hydrogen bond in this compound is reactive, and the boron and the hydrogen can add across double bonds. So let's look more closely at this. This is an interesting reaction, and it's unlike any that we've seen so far. And we're going to start by taking a look at borane itself. It's an interesting compound. In fact, boron chemistry is a whole field of chemistry by itself. Boron occurs so early in the periodic table that its compounds typically only have 6 valence electrons. So they are one of the exceptions, the common exceptions to the octet rule. So whether you have hydrogens bonded to boron or some other atoms, such as we see here in boron trifluoride. And these tend to be trigonal planar compounds, and they're characterized as being very good Lewis acids, and that's because the boron is effectively sp2 hybridized, but the p orbital is empty in these compounds. They have a structure that is analogous to that of a carbocation. In a carbocation, you have a positively charged carbon in a trigonal planar arrangement with an empty p orbital. Borane is a neutral compound that is trigonal planar with an empty p orbital, but that empty p orbital behaves the same way. It's a very good electron pair acceptor. Now, borane itself is actually a very complex substance. BF3 is known as a molecular compound, but free BH3, borane, is actually unavailable because it spontaneously dimerizes into a B2H6 compound. And the structure of that compound has been heavily studied because it's extremely unusual and contains these bridging hydrogen bonds. The structure, the structural aspects of this compound are a bit beyond the scope of this course, but it turns out from an organic chemistry point of view, we don't really need to understand the structure of this because we don't typically use borane as a free gas. We use borane in solution. So it turns out if you take diborane and you dissolve it in some kind of ether, you can use various types of ether. You can use tetrahydrofuran, you can use diethyl ether, just any kind of alkyl ether. When diborane is dissolved in those ethers, they form stable Lewis acid base complexes that are soluble in those ether solvents. And so you can purchase pre-made borane ether complex solutions. This is borane tetrahydrofuran complex. So why do I point this out? And the answer is because, at least from an organic chemist point of view, this stuff simply acts as if it were just BH3. And so we don't have to handle the flammable toxic gas. We can handle a much easier to manipulate liquid solution of borane. And it will, for all intents and purposes, act like we're working with just BH3. So how does this reaction happen? What's the mechanism by which borane adds to double bonds in a way where we end up with boron bonded to one of the double bond carbons and hydrogen bond to the other? So one possible mechanism would be similar to some of the things we saw before, where the alkene acts as a nucleophile, an electron pair donor, a Lewis base, and in this case, borane acts as an electron pair acceptor. And if we think about that simple interaction, then the immediate product of that should be a compound that has this structure where we've added BH3 and we formed a carbocation. And then you can imagine a subsequent step where hydrogen with the pair of electrons, so effectively a hydride atom, is transferred to that carbocation. Um, while we can draw that, such as we see here, it turns out there's no experimental evidence that supports this mechanism because there's no evidence that there is an intermediate formed in the reaction. So there must be some other mechanistic pathway that can be followed. It turns out all of the experimental data points to this being the mechanism, and that is a concerted addition of boron and hydrogen. Concerted meaning the boron and the hydrogen add at the same time across the double bond. So how do we push our curved arrows to indicate electron movement? And that's indicated here. We would say pair of electrons from the double bond, the pi bond, is used to form a bond to boron, and at the same time, the hydride, the hydrogen with this pair of electrons, bonds to the carbon. And you can think of a transition state that would look like this, where we're starting to break the pi bond, we're starting to move those electrons here to form a bond to boron, we're starting to break the boron hydrogen bond, and we're using those electrons to form the new bond to carbon. And all of our experimental evidence points to some sort of transition state that's something like this. And we're going to talk about some of the nuances of this because it's important. And so in one concerted step, the boron and the hydrogen add across the double bond. So thus the name hydroboration. So what experimental evidence tells us that the carbocation doesn't exist? Well, you might remember from our previous look at carbocation rearrangements that often we use experiments with this 3,3-dimethylbutene compound because it's very prone to carbocation rearrangements when this double bond is protonated or reacted with some species that produces a carbocation at this secondary carbon. Because as soon as you form a carbocation at that secondary carbon, you have the possibility of an alkyl shift. So if you take this dimethylbutene and you react with borane, what do you observe? And the answer is you observe exclusively this product A that you see here, where the boron adds this terminal carbon and that hydrogen added to the other carbon that you see here. If the stepwise mechanism had been taking place, that illustrated previously, and we form the carbon-boron bond and then have a subsequent transfer of hydride, which is indicated here, you have the possibility, because of this carbocation intermediate, of getting an alkyl shift and then the hydride being transferred at a carbon further down the chain. And we don't see any evidence of the existence of the intermediates, nor do we observe the product of rearrangement. So it seems that we don't form a carbocation, or if we do, it doesn't rearrange for some reason. The other thing we know about this reaction is that it is regiospecific. So if you have a carbon-carbon double bond that is differentially substituted on either end. So if you look at this example, we have a CH2 on this end, but the other end has a methyl and an ethyl group on it. What we observe is that the borane adds in such a way that you specifically get the boron added to the less substituted carbon and the hydrogen added to the more substituted carbon. And there seem to be two factors at play. One is illustrated here, and that is sterics, that it's sterically less congested to have the very small hydrogen add to the carbon that has the large alkyl groups on it. And the boron, be it small, it's a little more sterically congested because the hydrogen sticking off of it. The boron adds to the less substituted carbon. The alternative regiochemistry would turn the borane around, have the hydrogen add to the less substituted carbon and the boron added to the more substitute carbon. And we don't observe those. We always observe this sort of product. So it's adding in a regioselective way, and it seems to be, at least in part, related to sterics. It turns out there's another aspect, and if you think about the transition state a little more closely, electronics actually steers the reaction this way too. Because in the transition state, because we're taking electrons away from the carbon-carbon double bond and we're using them to form that bond to boron, we actually would have the development of a partial positive charge on one of the carbons. And that would be the carbon that the hydride ultimately adds to. So you can imagine two different possible transition states, here with the boron added to the less substituted carbon, and here with the boron added to the more substituted carbon. And that partial positive charge would be more stable on the carbon with the more alkyl groups added to it, for reasons we've discussed previously, hyperconjugation and the like. And so again, it seems that electronics is also steering us to this regiochemistry where the boron is adding to the less substituted carbon. Finally, one other aspect of this reaction is that because double bonds are essentially planar structures, if we look at the geometry of the double bond and the four things that are immediately attached to it, they all lie in the same plane because of the sp2 hybridization of the carbons and the pi bond. What we find is that in these reactions, consistent with the mechanism that we showed so far, that the hydrogen and the boron add to the same face of the double bond. And so we get a particular stereochemical outcome that we can observe experimentally. You can see that in a labeled compound such as this, where we have deuteriums in particular locations. We find that the hydrogen and boron add to a face, and we end up with those deuteriums with the same sort of relationship. Even more telling is if you do this with the cycloalkenes, you find that the products are indicative of the boron and the hydrogen adding to one face of that double bond. And this is known as syn addition. Syn means same side as opposed to trans addition on opposite sides. Again, our concerted mechanism can account for this syn addition. If these two things are adding at the same time, they have to add to the same face of the double bond because you simply can't wrap around to the other side to put the hydride on the other side. And so again, our transition state would look something like this, and leading to a product with a particular stereochemistry. Just to be thorough, the alternative, that carbocation mechanism that we really don't have any experimental evidence for, what would be the outcome of that if it were occurring? Well, you can imagine forming that carbocation intermediate, but at that point you can still get rotation. There's nothing to prevent the molecule from rotating. So this other end of the molecule can flip over, and you should get some scrambling of the stereochemistry. And so you would get a mixture of products if the carbocation were the intermediate. We don't observe that, so that's a little more consistent with the syn addition that we saw before. Finally, before we move on to kind of what we can do with these boranes, there's one other aspect of this reaction that's interesting, and that is that all three of these boron-hydrogen bonds are reactive, meaning that one molecule of BH3 can actually react with three molecules of alkene, and they all react in the same way. So if we look here, they have them highlighted. If we have this alkene undergoing reaction with borane, the initially formed product would have that regiochemistry that we just described, the boron added to the less substituted end of the double bond and the hydrogen added to the more substituted. And the product of that is what's simply generically known as an alkyl borane, where we've replaced one of the hydrogens with our alkyl group here. But we still have two hydrogens attached, and this borane is also trigonoplanar with an empty p orbital. It is still a powerful Lewis acid, and these boron-hydrogen bonds can react again. And so we can get a reaction of a second equivalent of our alkene with one of those bonds. This leads to a dialkyl borane. And finally, that last boron-hydrogen bond can react further. And the end point of this reaction are these trialkyl boranes. All right, in and of themselves, the trialkyl boranes aren't terribly interesting, but what's useful about them is that they can be transformed into other things. And we're going to look at one of those transformations that's particularly useful to us, and that is that they can undergo oxidation. And the oxidation replaces the carbon-boron bond with a bond to a hydroxyl group. And these are very simple oxidations. We're actually just using hydrogen peroxide with a little bit of base added to it. So it's a very mild, simple reagent to use. And this hydrogen peroxide is essentially the same as what you would buy at the drugstore. Um, and these trialkyl boranes are converted into alcohols. What happens to the boron? It ends up in the form of this boric acid compound. And so here below, we see some kind of previously synthesized trialkyl boranes. This one has 3 butyl groups treated with hydrogen peroxide base in water. And we end up forming these 3 1-butanol and the boric acid over here. This last example is a little more informative about exactly what's going on, because here we have a trialkyl borane. Notice the 2 R groups. Those 2 R groups would be identical to the structure you see here. This hydroboration must have been to the double bond in the ring, and so we had the syn addition of the hydrogen and the boron. And in this example, we can see the stereochemistry of the oxidation. And the stereochemistry of the oxidation is such that the stereochemistry of the boron is retained in the stereochemistry of the hydroxyl group in the alcohol product. And that's an interesting outcome. So let's look more closely at how this happens. And this is perhaps the most mechanistically complex thing that we encounter in this chapter. So here's the mechanism of the oxidation. So follow me through this. So trialkyl boranes are structurally analogous to borane itself. We just have now alkyl groups where the hydrogens were present in the borane, but we still have an empty p orbital because it's a borane compound. Basic hydrogen peroxide includes peroxide ion. What the base is doing in that solution is deprotonating a little bit of the hydrogen peroxide. Peroxide ion is a very good Lewis base, and as we've talked about, boron compounds are very good Lewis acids. And so we get a Lewis acid base reaction where the peroxide simply adds to the boron to form a structure that looks like this. Once that addition occurs, you notice that we get a change in hybridization. The boron goes from sp2 to sp3. But this structure is not stable. And a curious thing happens, and that is that one of the alkyl groups with its pair of electrons migrates to oxygen. It's almost like an alkyl shift. But in this case, the migration is accompanied by loss of hydroxide. And normally we don't see hydroxide as a leaving group, but this isn't a normal compound. This is a peroxide, and those oxygen-oxygen bonds are actually quite weak. So the alkyl group migrates with the loss of hydroxide, and that's a concerted process. Those 2 things happen at the same time. And so that initial migration essentially inserts an oxygen between the boron and the alkyl group. Well, this can happen to the other alkyl groups in the same way. So we get another addition of peroxide to the boron, another migration of alkyl group, and then it happens a 3rd time. And so that's what's indicated here, that this initially formed compound undergoes addition, migration of alkyl group, and loss of hydroxide 2 more times. And you end up with this compound, which is similar to what we started with. We've just inserted an oxygen into the boron-carbon bonds. And this is known as a boronic ester. But under those conditions, the boronic ester isn't stable, and it actually undergoes a hydrolysis, and that step is shown here. And we're not going to go into the mechanistic aspects. It's a little bit complicated, but essentially we're hydrolyzing these boron-oxygen bonds, producing the boric acid from the boron and protonating that oxygen to give us a hydroxyl group, and we make alcohols. So let's think about the overall process, this being a two-reaction sequence. The hydroboration to form the trialkyl borane, followed by oxidation. And as a practical matter, by the way, you can do this in the laboratory right in one reaction vessel. You can do the hydroboration, and without working up the reaction or purifying anything, you can just add basic hydroperoxide right to the reaction mixture and carry out the oxidation all in one flask. But here it is broken down. Here we have an alkene. It's an unsymmetrical alkene. We would expect boron to add to the less substituted carbon, hydrogen to this. We would get three equivalents of alkene reacting with our borane, and here's the product of that. So here's our trialkyl borane. So each one of these fragments was derived from the alkene. And then we add peroxide, and we're going to insert oxygen and then hydrolyze where these carbon-boron bonds are. And as a result, we're going to get alcohols that look like this. So now let's think about this. We've effectively added water. We've done essentially the synthesis of an alcohol from an alkene, and where we've overall added hydroxide to the less substituted carbon, hydroxyl group, and we've added a hydrogen to the more substituted carbon. Here's the hydrogen that we added from the borane, and here's the hydroxyl group that we got after the oxidation of the trialkyl borane. And if you think about that, that's actually the opposite regiochemistry of the hydration reaction we learned much earlier, where we use water and acid. If we were to take this starting alkene and treat that with water and an acid catalyst, we would expect Markovnikov addition, hydrogen adding to the carbon with the most hydrogens and hydroxyl adding to that more substituted carbon. This is the opposite regiochemistry, and it's known as anti-Markovnikov addition. So the net result is just that. So this is an interesting tool. We have the means of hydrating this alkene in a way that puts the hydroxyl group on the more substituted carbon, and then using hydroboration oxidation in tandem, we have the means of hydrating that alkene and putting the hydroxyl group on the less substituted carbon. So here are two real-world examples of that. And if you want to think about the overall transformation, you would use borane. Typically, it's in some sort of ether solvent. You would treat that then with hydrogen peroxide in base under aqueous conditions. The net result is add hydrogen to the more substituted carbon, hydroxyl group to the less substituted carbon, and we get net anti-Markovnikov addition of water. If you look at the second example, we would expect the hydroxyl group to add here at the less substituted carbon and the hydrogen to add here at the more substituted carbon. We would also expect in this particular example to see syn addition in the stereochemistry of the product. And that's indicated here. We would get this compound where the hydroxyl group is trans to the methyl group, and we would get that as a racemic mixture. So I want you to prove to yourself that this is the correct stereochemical outcome of that sequence of reactions in there. All right, that finishes chapter 10. Here you find the usual list of problems that I recommend that you focus your attention on while you're studying.